Hi, everyone. Welcome to week 4 of online learning. We are going to talk about kinetics today. So what is kinetics? It's the study of the rate of a reaction. So how long does it take for a reaction to go? Rate, like anything, is going to be a change in something over time. When we talk about kinetics, we look at the change in the concentration of reactants over time. So there are many different measurements that you can take for concentration changes. Depending on what phase you are in. For gases, you can measure a change in volume. You could also measure a change in pressure. For solutions, you can measure a color change or a change in concentration. Now, a color change, you use a spectrophotometer or a colorimeter. We never got to do the solutions lab. We would have used one there so we could have seen concentration and how it works, but Corona, I don't know. For solids, you can measure a change in mass. Now, there are different factors that affect the rate of a reaction. The collision theory, which is very important stuff, states that the rate depends upon the collisions of particles. So that's why in a reaction, you want to stir it because we're going to have more collisions and therefore more reactions. A couple of ways we can increase the rate. We can increase the exposed surface area by breaking up a solid. So if you have a sugar cube versus granulated sugar, the granulated sugar will dissolve more because there's more exposed surface area. You can increase the concentration of the solute so that there are more particles. More particles lead to more collisions, so it leads to more reactions. We can increase the reactivity of reactants, and we can increase the temperature, which will increase the number of collisions, because we know the more energy, the higher the temperature, the more energy, the faster those particles will move, and the more likely they are to collide. But it is important to note, critical information here, collisions alone don't cause a reaction. Particles must have the proper orientation and enough energy to break and allow for rearrangement to form new bonds. So just because they hit doesn't mean it's going to work. They have to hit in the right way and with the right amount of energy in order for the reaction to actually occur. So the activation energy, E sub A, is the minimum energy required for a reaction to occur. We know a catalyst is a substance that speeds up the rate of the reaction, and it does this by lowering the activation energy. So if we had an energy diagram, an enthalpy diagram, that would be, this is the reactants, this is the products. We know that that would be endothermic. And if we had a catalyst, what it ends up doing is it lowers this hump. So now my activation energy has just gotten smaller. And over here, it would look like this. So we can see our E sub A, the activation energy, would be smaller, allows the reaction to occur faster. So another vocabulary term here, activated complex. The activated complex is at the top of the peak. So it's the high energy arrangement of reactants where bonds are broken and elements have rearranged, but they have not formed a new bond yet. So what happens? The energy goes in to break those bonds. We're at the very top of the peak and my potential energy is the highest. Energy, once those bonds start to form, energy is given off and then you go down that side. So that would be an enthalpy diagram having to do with a catalyst. And this is the bulk of this. Our differential rate law, excuse me, shows how rate depends upon reactant concentration. So if I have a general reaction where A and B capital are the reactants, X, capital X is the product, the lowercase letters are going to be the subscripts, the rate law, rate will be equal to K, which is a rate constant, the concentration of A raised to M times the concentration of B raised to N. M and N are rate orders, okay? Very important stuff here. What are rate orders? There are 3 rate orders that we're going to talk about: 0 order, 1st order, and 2nd order. A 0 order occurs when the concentration and rate have nothing to do with each other. So there is no, if something doubles, one thing stays the same. There is no correlation between the two. A 1st order occurs when concentration and rate are directly proportional. Concentration doubles, rate doubles. Concentration cuts in half, rate cuts in half. They are proportional directly. And then a second order occurs when the concentration and rate are exponentially proportional. For example, if the concentration doubles, the rate will quadruple. Okay. Now, how do we use this? The important part. Here, we've got a data table full of information. And so we're going to look at any kind of question that you could possibly see with a kinetics question based on this data table. So experiments were performed involving reactants A and B, and the following data was collected. So we have our initial rates and our initial concentrations. So the brackets and then the lowercase 0, that means the concentration initially. So use the data above, determine the order for the reaction in respect to each of the reactants, and you must include a justification. And the justification part is very important. So I'm going to show you how to do this, and I'm going to show you what you need to write in order to justify it. So if I want to look at the rate order for B, I need to look at two trials. No, I'm sorry. If I want to look at the rate of A, I need to look at two trials where B remains the same. Okay, so B remains the same in trials 1 through 3. I want to look at trials where it's easy. That math is easy. So if we look at the concentration of A from 1 to 2, that doubles. Okay, so the concentration doubles. What happens to the rate? Well, from 1 to 3, the rate stays the same. Those are unrelated to each other. No relation. So that means that A is 0 order. There is no relationship between the rate and the concentration for A. What about B? For B, we look at two trials of A that remain the same. So that's either 1, 4, and 5. Well, the easiest way, look, I don't know what the rate is, the initial rate is for 5, so I can't use that. So, and the math works out easy. From 1 to 4, that's times 2. From 1 to 4, that's also times 2. So B is first order because that is directly proportional. Those are my answers. My justification, I'm going to scroll down and write it here, and then I'm going to have to erase it. So when you need it, feel free to just pause so you can write it out. Arrows on your data table are not going to work. So there are two ways to do this. There is one mathematically. I'm not going to show you the mathematically one. It's not hard, but it's harder than the way I'm going to show you. So we need to write out a statement. This is what I would write down exactly. So in experiments 1 and 3, the concentration of B remains the same. That's what I did. I looked at two trials where B remained the same so I can figure out A. I can't have two things changing or else the math isn't going to work. So that's my first part. Now we talk the concentration of A doubles while the rate remains the same. Slash unchanged. Therefore, A is 0 order. That would be my justification. That's exactly what I did, and it's just explaining what those arrows are doing. Now for the other one. In experiments 1 and 4, again, the concentration of A remains the same. The concentration of B doubles while the rate doubles. Therefore, B is first order. those are my justifications for this. Okay, so pause so you can write that down. I'm going to go back up and finish the problem. So now I can write my rate law expression. My rate law expression, rate is equal to K, so that's my rate constant. A is to the 0 order. When I raise anything to 0, it becomes 1, so I'm not even going to write it. Concentration of B, it's to the first order. I don't need to write a 1. There's my rate law expression. Now, what I can do is I can, for the next one, determine the constant just by taking the values from my data table and plugging them in. I just used the first one. It doesn't really matter. They should all work and give you the same answer because K is the same when you're at the same temperature. And so I'm just going to plug it in, 0.50 times 10 to the negative second. Units, important, moles over liters times hour. That will be equal to K times the concentration of B, 0.20. Divide both sides by 0.2, and K will equal 0.025 units. This is molar, which is moles over liters. So when I divide by a fraction, I multiply by the reciprocals. How the units will work, you'll end up doing moles over liters times hours times liters over moles. Liters cancels, moles cancel. Your units are inverse hours. You need to make sure that you do that math with the units every time. When you do a problem like this, you'll always get 1 point for the answer, 1 point specifically for the units. Okay. For the overall order of the reaction, all you have to do is add up all the orders. And in this case, it was 1 plus 0, so the overall is going to be 1. And then finally, I want to figure out what is underneath this black box. And I'm going to erase this information here so I have some room. So we can do this math. So now I know what my K is. I have my rate law. So I can just plug everything in and I'll be able to solve. So again, this is my rate law expression. I'm trying to solve for the rate for experiment 5. So I'm going to say rate, because that's what I'm solving for, is equal to my K, 0.025 inverse hours, multiplied by the concentration of B, 0.60, that'd be molar, which is moles over liters. And so I do that math, it gives me 1.5 times 10 to the negative second, moles over liters times hours. You could write it a lot of ways. You could do molar over hours. Actually, those are the only 2 ways you could do it, but that's it. Units are very important when you're doing this stuff with the rate laws, but you can also see that the initial rate units are given to you there. Make sure you check the assignment for this week. And this is actually it for this unit. Next week, we'll be starting the very final stuff, which is going to be acids and bases, I think, and equilibrium. So be on the lookout for that, and let me know if you have any questions. All right, I'll see you next week.